So, in our last class, I have introduced the notion of temporal logic and I have talked about the temporal operators. Basically, we can categorize the temporal logic in two different ways. One is your past temporal logic and second one is your future temporal logic. And in future temporal logic, we can have or we have discussed about the notion of four temporal operators. One is your next, second one is globally, third one is future and fourth one is your until operator, which is a binary operator. In this class, today I am going to introduce a special class of temporal logic, which is known as your CTL, computational tree logic. So, I will see what is a general notion of your temporal logic and what is CTL. And after that, we will go for syntax and semantics of CTL, and after that I will give some example how to represent those things with CTL. So, in temporal logic what happens? We have seen that we are going to give the meaning of a temporal logic operator with respect to a model. Okay. So, you can have a model which is nothing but a sequence of states, and we are going to give the meaning of a temporal operator in a particular state. So, we say that if I am having a model M and I am having states as this particular combination model a temporal operator phi, temporal formula phi. Now, we are having two notions, one is called path formula and second one is called state formula. Now, just see that in last class what we have discussed, that we are having some state, it is a sequence of state like that. States are marked as S1, S2, S3, S4, S5, S6 like that, and say that in S5 we are having that atomic proposition P is true. Then what happens? I can say that in state S1 the formula F P is true, in future P is true. So, though we are talking about a state S1, but it is related to this particular execution sequence. So, in case of linear temporal logic, what happens? We are having one part and we are going to reason about that particular part. But already I have mentioned that we are having the notion of your branching time, where time branch out in several directions. So, in that case, we are going to look for all possible paths or there exist a path. So, in this case what will happen? We are going to talk about the state formula. Here in notes general we said that this is in this particular part for state S1 that F P holds. Now, in case of branching time what will happen? We just see that we are having a state S0, depending on several conditions, then time may branch out in several different position. So, if I am coming to S1, depending on the input combination or state of the system, it can proceed either S2 or S3. Now, when we are going to talk about in state S0, we have to see all possible combinations. Say this is say path pi 1, so this is path pi 2 and this is path pi 3. So, in that particular case, we have to see the nature of this particular temporal formula in all those possible paths, and depending on that we are going to say the behavior of that particular formula phi in this particular state S0. So, in this case we are going to say that it becomes a state formula. So, now we are going to talk about a particular class of temporal logic which is known as your CTL, computational tree logic. So, in computational tree logic, it is a branching time logic. We have to look for all possible paths, and when from a particular path we are going to look into all possible paths, then we are going to say that that particular formula is true in a state. So, we are going to talk about state formula in case of CTL. So, now you just see that computational tree logic, it is a branching time logic, and we are going to define the meaning of this particular CTL or computational tree logic with respect to a model. Now, just see in this particular example, say I am having this particular model M, it is having three states, say S0, S1 and S2, and we are having some transition. Just you consider this transition, say S0, it is going to S2 by this particular transition. When we are having in your S2, either we can go to S3 or we can go back to S0 again. So, in this part it can have a transition like from S0 to S2, S0 to S2 like that. Now, in this case what happens, this is a graph representation, we can unfold this particular transition system and we can get at some sort of tree. Now, if unfolding of this particular situation, you just see that we are in this particular state S0, depending on the scenario either we can go to S2 or we can go to S1. So, these are the next state behavior. So, this is your in S0, we can come to S1 or we can come to S2. Now, when we are in S2, again we are having two choices, either we can go to your state S1 or we can go back to state S0 again. So, behavior of this particular state S0 and this particular state S0 is almost same, or they are same basically apart from their timing instance. If we can look into timestamp, in some timestamp T0 we are over here, then in T1 I am going to be in this particular place T0 plus 1 and next time instant in T0 plus 2 we are in this particular. So, apart from this particular timestamp, all the behavior of this particular state S0 and this particular state S0 is same. Now, in case of computational tree logic, we are going to reason about this particular formula over a tree structure. That is why the name coming as your computational tree logic. So, eventually if we are having a state transition system like that, we can unfold it to a graph and we can assign the meaning of CTL with respect to this particular tree. So, we are going to say this is your computational tree logic. Now, we are going to see how we are going to define the CTL formulas. Now, first when we are going to look for a language or look for a logic, then we have to look for the syntax of that particular logic. So, what is the syntax of that particular logic CTL? So, when we are going to write a formula LCTL, then it involves several components. The first component is your atomic proposition. So, we are having a set of atomic proposition, these are represented as a say P, Q, R, S like that. So, this atomic proposition is going to take truth values either true or false like our propositional logic. So, this is basically proposition that we have, the truth values of these particular propositions are either true or false. Next, we are having part quantifiers, and the part quantifiers is basically represented A and E. A means that in all possible path. So, in a particular state, if you go for all possible paths, then we will going to quantify it by this particular part quantifier A. Similarly, E is another part quantifier which says that there exists a path. If we are interested for a particular path, then we will look for this particular there exists quantifier. After that, we are having all the propositional logic operators that we have in propositional logic can be used in our temporal logic also. So, like that AND or conjunction or disjunction, not, negation, or maybe your exclusive or like that your implication, all those particular temporal propositional operators will be used in our temporal logic also. So, these are basically similar to your temporal propositional logic. Apart from that, we are having temporal operator. We are going to use the temporal operator in our CTL. So, the temporal operators that we have discussed are used in this particular CTL also. So, these are the four temporal operators that we are having. X stands for your next state, F stands for in future, G stands for globally it holds, and U stands for until operator. So, P until Q. So, it is a binary operator, P remains true until Q becomes true. So, these are the components that we are going to use while defining the CTL formulas. Now, in BNF notation, we can define the CTL formulas like that. So, we are using two symbols, one is your bottom and second one is your top. So, this top and bottom are used as our CTL formulas. Top stands for the truth value true and bottom stands for the truth value false. So, we are having two truth values in our logic, one is your true and second one is your false. So, true is represented by the symbol top and bottom is represented by the symbol false is represented by this symbol bottom. So, top and bottom are treated as your CTL formula. then next we are having P, all P will be treated as your CTL formula. What is P? P are nothing but these are the proposition that we are going to use in our system. So, we are having some proposition, those proposition can take values either truth values either true and false, all these proposition will be treated as your CTL formula. Now, we can use the propositional connectives to form CTL formula. So, if phi is a CTL formula, then not of phi will also be a CTL formula, phi and phi will also be a CTL formula, phi or phi will also be a CTL formula, phi implies phi will also be a CTL formula. So, all propositional connectives will be used to define CTL formulas from CTL formula. Apart from that, we are having temporal operators, so with these temporal operators are also going to form some CTL formula. So, the temporal operator next state. So, we are having next phi as our temporal formula. If this temporal formula is preceded by part quantifier A or part quantifier E, then we are going to say that these are CTL formula. Similarly, for fusor operator, we are going to have A f phi and E f phi. That means, with part quantifier A and E, we are going to get two CTL formula. Similarly, for globally also G phi, so we are going to have two CTL formulas A g phi and E g phi. Next, we are going to have until operator, which is a binary operator. So, if we are having two CTL formula phi and phi, then we can say that A phi until phi will also be a CTL formula, or E phi until phi will also be a CTL formula. So, we can construct CTL formula using those particular rules. If the formula conform to these particular rules, then we are going to consider those as our CTL formulas. Others will not be treated as our CTL formulas. Now, by looking into this particular BNF notation, now we are going to see what are the CTL formulas that we are having. So, first we are going to say that we are having a set of atomic proposition. So, P is a set of atomic proposition. We can say that P, Q, R, etc. are atomic proposition. So, they can take root values either true or false. Now, we can define the CTL formula with the help of this atomic proposition. Now, every atomic proposition will be treated as a CTL formula, because in BNF notation also we have seen that all atomic proposition will be treated as a CTL formula. So, if P is an atomic proposition, so in this case we will say that P is also a CTL formula. Now, for all atomic proposition we are going to get CTL formula. Now, you just consider that if we are having two CTL formula F1 and F2, because recursively we are going to define it. So, if we are having two CTL formula F1 and F2, then we are going to say that not of F1 is also a CTL formula, F1 and F2 is also a CTL formula. Similarly, we can say that F1 or F2 is also a CTL formula. Then AX F1 is also a CTL formula, EX F1 is also a CTL formula, A F1 until F2 is also a CTL formula, E F1 until F2 will be also a CTL formula. So, similarly, AG F1, EG F1, AF F1 and EF F1 will be CTL formula. So, this way we can construct our CTL formula. So, what are the meanings now? You just see that if you look into these particular formulas, we will find that the meaning of those particular formulas with propositional connectives are very straightforward. Now, we will see what is the meaning of those particular temporal operators. So, one is your AX F1. What does it means? That means, if we are going to look for a particular state, it is having several possibilities in future. In all those possibilities, in next state, if F1 holds, then we will say that AX F1 holds at that particular point or particular state. That means, what we say that in a particular state AX F1 holds if in all possible next state F1 holds. So, that is why it says that this holds in a state S0 if F1 holds in all successor state of your S0. Similarly, EX F1, it means that there exists a successor such that F1 holds. So, it is having several possibilities in future, but we are concerned about a particular direction or in a particular future. So, if in the next state it holds, then we can say that in that particular state EX F1 holds. Similarly, A F1 until F2. So, F1 that until is a binary operator. So, we need two formulas F1 and F2 and that is quantified by part quantifier A. In this it means that always until, that means in all possible direction, in all possible path, F1 must holds till F2 holds. So, this is A F1 until F2. Similarly, E F1 until F2. So, we are concerned about a particular path or there exists a path, not any path we are looking into it, one particular path. So, if we get such a path that F1 holds until F2 holds, then we say that in that particular state E F1 until F2 holds. A G F1, this is always globally F1 holds. So, if we are in a particular state, wherever we go in all direction, in all paths, in every state F1 must holds, then we will say that A G F1 holds. Similarly, E G F1, this is concerned to a particular path. So, we are having several possibilities, but we will look a particular path and in this particular path in all states F1 holds, then we say that in that state E G F1 holds. Similarly, A F F1, this capital F stands for a future operator or eventually operator. So, that means F1 holds in all path in future. So, we should get a future state where F1 holds, then we say that A F F1 holds in that particular state. So, we have to look for all paths. So, similarly, E F F1 it looks for a particular path. So, if any path in future F1 holds, then we say that E F F1 holds. Now, you just see that we are having this particular 4 temporal operators and these particular 4 temporal operators will be preceded by part quantifier A and E, and that means we are going to get 8 different combinations and we are going to get 8 different temporal formulas. And the meaning of those temporal formulas will be defined over a model. Formally, we are going to define the semantics. Just I am giving a brief idea about it, how we are going to say that this particular formula is true. Now, you just see that if you look into this particular syntax, then what will happen? You will find that in CTL, every temporal operator must be preceded by a path quantifier. So, we are having say 4 temporal operator X, future, globally and until. In CTL, this particular 4 temporal operator must be preceded by path quantifier A or E. Then only we are going to say that these are CTL formula, and due to this particular quantification by path quantifier, the CTL formulas are basically state formulas. We are going to define the truth values of a CTL formula over a state. So, just simple like that I am going to say that if I am in a state S0, so it is having 3 possibilities in future. This future are say S1, S2, S3. If we come to S1, say I am having 2 different future possibilities. So, this is your S4 and S5. Like that we can have future possibilities in all these directions. Now, when we talk about CTL formula, the truth values of this CTL formula will be defined over this particular state. So, it is a state formula. So, any temporal formula say F P, in what it says that in future P holds. So, this is a temporal operators temporal formula, and basically this temporal formula defines over a path with respect to a starting state. But when we are going to talk about CTL, that means I can say that it will be A F P. So, this is the temporal formula F P is preceded by this particular path quantifier. So, we are going to have this particular formula which is a valid CTL formula, and the truth value of this particular CTL formula will define over this particular state or any state. So, if we talk about this S0, say this is my model M. So, model M in state S0, whether it models your A F P or not. That means, this CTL formula, truth values of this CTL formula is defined over this particular state. So, CTLs are your state formula, and what we can say which one is a CTL formula? If every temporal operator is preceded by a path quantifier, then we say that this is your CTL formula. Now, after looking for the syntax of the CTL formula, let us see some formulas and let us see whether these are CTL formulas or not. So, you consider about this particular first formula. Now, what will happen? You can say that in this particular case, we are having a set of atomic proposition P, say P, Q, R. These are set of atomic proposition. These are having the truth values either true and false. Now, every atomic proposition will be treated as a CTL formula. So, in this particular case, I can say that Q is a CTL formula. So, north of Q is also a CTL formula. Similarly, P is a atomic proposition. So, P is also a CTL formula. Now, G is a temporal operator. It is preceded by E. So, E, G north of Q is also a CTL formula. So, if we are having phi as a CTL formula, then what will happen? North of phi is also a CTL formula. So, in that particular case, north of E G phi is also a CTL formula. So, P is a CTL formula and north of E G north Q is also a CTL formula. These two CTL formulas are connected with the help of this particular implication operation. So, this whole set is going to give you a CTL formula. Now, this CTL formula is again quantified again having a temporal operator called G. So, whether globally these holds or not, again this particular globally temporal operator is preceded by this part quantifier S. So, that means this whole formula is a CTL formula. Now, similarly, we can analyze each and every formula and you will find that these are valid CTL formula. So, here in the second example, you just see that this is your Q until R. This is until operator, Q and R are CTL formula. So, E Q until R is also a CTL formula. Similarly, E G P. So, P is a CTL formula. So, E G P is a CTL formula. Now, if we look into it E G P E Q R, then you will find that this particular operator E is not is a CTL formula, but it is not directly connected to it, because after P we are having E. So, in that particular case it is not a CTL formula, but we can very well make it CTL formula by putting some binary connectives or say a proportional connective. If I say that this is odd, then it becomes a CTL formula. So, E G P it is a CTL formula and E Q until R another CTL formula, because this E until your temporal operator is preceded by this particular E quantifier, part quantifier. Similarly, G is preceded by your E part quantifier. So, this whole formula becomes a CTL formula. Like that you can analyze other one also. So, the fourth one I am going to say, P is a atomic proposition. So, it is a CTL formula. F is a temporal operator and it is preceded by part quantifier. So, E F P is also CTL formula. Q is also a CTL formula, because it is an atomic proposition. So, they are connected by this particular conjunct. So, this whole thing is also a CTL formula, and already I have said that if phi is a CTL formula, then north of phi is also a CTL formula. So, north of E, F, P and Q is also a CTL formula, and this CTL formula is again having a temporal operator G, which is preceded by A. That means, in all part globally whether this holds or not. So, this whole formula is also a CTL formula. So, like that we can check each and every formula and we will find that these are valid CTL formula. Now, look for this another set of formulas. The first formula is G P. So, in case of your G P, you just see that P is an atomic formula. So, it is a CTL formula. G is a temporal operator. So, G P is a temporal formula, but this temporal formula is not preceded by any part quantifier A and E. Since it is not preceded by any part quantifier, so this temporal formula is not a valid CTL formula. So, we are not going to say that this is a CTL formula. Similarly, second example you just see that R is a CTL formula, since it is a atomic proposition. So, G is a temporal operator. So, GR is a temporal formula. FGR, now F is a temporal operator, G is a temporal operator and R is a CTL formula, because it is atomic proposition. So, this particular temporal operator G is not preceded by any part quantifier, directly we are getting F. So, this FGR is a temporal formula, no doubt, but it is not a CTL formula. Since it is not a CTL formula, so EFGR is also not a CTL formula. So, to have, or we say that it will be a CTL formula provided each temporal operator is preceded by your path quantifier, and with the help of this path quantifier we are making, or we will say that the CTL formulas are state formula. We are going to talk about the truth values of a CTL formula over a state. Now, similarly, this next formula, if you see that R until Q. So, until is a your temporal operator, R until Q is a temporal formula, because he is a until operator. So, this temporal operator is not preceded by any path quantifier. So, it is not a CTL formula, but if we say that E R until Q, then it becomes a CTL formula, because this temporal operator is your preceded by your path quantifier. So, F R until Q is not a temporal formula, but we are saying that this is a temporal formula. But since it is a temporal formula, so I can say that F and this temporal formula. If I write this thing, then it will become a temporal formula, but it is not a CTL formula now, because this particular temporal operator F is not preceded by any path quantifier, but I can make it a temporal formula, CTL formula, by placing a path quantifier in front of it. So, this whole formula becomes a CTL formula. As such, this particular third formula is not a CTL formula, but it is a temporal formula. But if I put path quantifier in front of every temporal operators, then it becomes a CTL formula. So, with similar argument, you can say that this equation 4 or say expression 5 are also not a CTL formula. You just see that you can apparently you will find that this may be a CTL formula, because it is preceded by your this particular path quantifier A. But if you look component wise, first look into this particular component P until R. This is a temporal formula, but it is not CTL, because this particular until is not preceded by any temporal path quantifier. Similarly, R until Q is also temporal formula, but this is not a CTL formula, because this until operator is not preceded by any path quantifier. So, that is why this, since these two components are not a CTL formula, so their conjunction will not also be a CTL formula. So, in that case we will say that this is not a CTL formula. So, now we have seen the syntax of our CTL computational tree logic. We can use atomic proposition. All atomic proposition will be treated as our CTL formulas. CTL formulas can be connected by your propositional connective like AND, OR, XOR, implication, etc., and those will become form CTL formula. Again, if we are having any CTL formula, they can construct another CTL formula by temporal operators, but each and every temporal operators must be preceded by a path quantifier. Then only we will say that this is a CTL formula. Without preceding by a path quantifier, we are not going to get CTL formula, but we may get temporal formula. So, CTL is a subclass of my temporal formula. So, with path quantifier we are making CTL formulas. Secondly, when we are going to say that path quantifier, basically we are going to say that it path quantifier A say that in all possible path from a particular state S, or E says that there exists a path from a particular state S. So, in that particular case, this CTL is treated as our state formula. So, we are going to look for the truth values of CTL formula with respect to states, but which should have in either all possible computational path or there exists a computation path. This is the meaning of A and E. So, with the help of path quantifier A and E, we are making them the state formula. Now, we have to look for the semantics or meaning of this particular CTL formula. Already I have mentioned that if we are going to look for a truth values of a temporal formula, it is always defined over a model. So, for CTL also we have to define the meaning of CTL formulas over a model. So, in this particular case we are going to have a model M called M, and this model is having three components. So, this model M is defined as S, this arrow and L. So, we are going to have a model which is a three tuples. Basically, we are having three basic components S, we are talking about one arrow and we are talking about L. With the help of this, we are going to define a model, and in this particular model, we are going to define the meaning of our CTL formula. Now, what are the three components? Just see the formal definition of this particular temporal structure. So, we said that a temporal structure M is having a 3 tuple, where we are having 3 components S, arrow and L, where S is a set of finite states. That means, we are having states, in these states is a finite state. So, we are having finite number of states in our set. So, we are representing it by S. The second one, that arrow that we are representing, it is a transition relation, and transition relation is nothing but a subset of Cartesian product of S and S. That means, we are having a transition from one set to the other state. So, that is why what we are saying that it is a subset of this Cartesian product S and S. So, Cartesian product S and S basically give me the components like that S 0 and S 1. Say if S 0 and S 1 say belongs to your say S, then S 0 S 1 will be a component in our this Cartesian product. What does it mean? That means, we are having a transition from S 0 to S 1. So, the second component is the transition relation, which is a subset of the Cartesian product of S and S. With a particular restriction, it says that for all S belongs to S, there exists an S dash such that S dash belong to this particular transition relation. Now, what does it mean? So, if we are having a set, from that particular state, we should have a transition to some other states. That means, it says that the transition relation is complete. So, this is one restriction, the CTL structure that we are defining over here, the transition relation must be complete. That means, if you pick up any random any state S, it must have a successor state. If some states are not having successor state, then we are not going to treat these things as a CTL structure. Along with that, we are having a labeling function, which is known as basically L, defined as L. It is nothing but S arrow row of V. Basically, what is V? Here V is basically this is set of atomic proposition, and rho V basically says that power set of this particular set of atomic proposition. So, we will give an example. So, the states will be labeled by the set of atomic proposition, and what is saying that set of proposition variable, and these are atomic formulas or atomic variable. So, what basically this labeling function says? It says that this particular atomic proposition is true in this particular state. So, we are having a labeling function, because we know since these are atomic proposition, we know the true values of those particular atomic proposition, either they will be true or they will be false. So, if a particular atomic proposition is true in a particular state, we label this particular state by that particular atomic proposition. And this structure is often called Kripke structure. So, basically the semantics of your CTL formula is defined over Kripke structure. We use the term Kripke structure. So, this is a Kripke structure which is having these 3 components S, transition relation and L, and what is the basic requirement? One is your transition relation must be complete. For every state, there should be a successor state. So, we are going to define it over a Kripke structure, and if you look into the behavior of the Kripke structure, you will find that it is nothing but very much similar to your state transition diagram. It is a state transition diagram, and in this particular state transition diagram, we are having 2 restrictions. One is your all state must have at least one outgoing S, that means, every state must have a successor state, and secondly, we are having a labeling function. The states will be labeled by the atomic proposition where this particular atomic proposition is true. Okay, we will just see one example, then it will be clear. Now, you just see that come back to this particular transition diagram. So, it is a finite state transition diagram, because we are having that state S. What are these particular states? We can say that this is your S 0, S 1 and S 2. So, we are having 3 states. Along with that, we are having the set of atomic proposition P. Here we are having the state of atomic proposition, or the atomic proposition that we have are A, B and C. This atomic proportion get two values, either true or false. Along with that, we are having this particular transition function. So, here what is the transition function that we have? We are having a transition from S 0 to S 1. So, we are having S 0 to S 1, this is a transition. On the notation, I can say that since I am saying that it is a subset of Cartesian product, I can say S 0 S 1 also, I can write like that. Again from S 0 to S 2, I am having another transition. So, I can say that that transition set have S 0 to S 2. Now, when I come to S 1, you will find that we are having a transition from S 1 to S 1. So, S 1 to S 1, we are having another transition. Now, only one transition we have. And similarly, when we come to this S 2, then we will find that from S 2, we are having a transition to S 0, and again another transition we are having from S 2 to S 1. So, this set of transition relation basically contains this particular 5 transition 1, 2, 3, 4, 5. Now, it should satisfy one condition that this particular transition relation must be complete. That means, every state must have a successor state. Now, if you say that if you look into state S 0, we will find that it is having at least 2 successor states. If you look into S 2, again it is having 2 successor states. If you look into S 1, it is having a self loop. That means, we are having a S 1 as its own successor. That means, it is complete. Now, along with that, we should have a labeling function L. So, what is this labeling function? It says that we are going to label each and every state by the power set of this particular set of atomic variables. So, in a particular state, if the atomic variable is true, then we are going to label it by this particular atomic proportion. So, here it says that the L of your S 0 is basically nothing but A and B. So, what it says, in when we are coming to this particular state S 0, then this atomic proportion A and B is true, and indirectly it says that in this particular S 0, C is not true. That means, we can say that not of C. That means, we can say again label it by not of C also. It says that means not of C is not true in this particular state. But in convention, what we say that if it is not labeled with any atomic proportion, we say that this atomic proportion is false in that particular state. Similarly, this particular state S 2, it is marked with B and C. That means, the atomic proportion B and C are true in this particular state S 2, but atomic proportion A is false over here. And in S 1, it is labeled with C. So, it says that the atomic proportion C is true in this particular state S 1, but atomic proportion B and C are false over here. So, if atomic proportion is false, we generally never marked it, but internal meaning is that this atomic proportion is false in this particular state, because atomic proportion can have two truth values, either true and false. If it is true, we are labeling it. If we are not labeling it, it says that this atomic proportion is false in that particular state. Now, just look into this particular model. So, I am saying this is M 1 and this is M 2. Whether these two models are Kripke structure. So, both are having that similar structure, it is having similar state, and we are talking about a transition only. Labeling function, we are not showing it over here, because we are not talking about the set of atomic proportion. But if you look into these two models M 1 and M 2, whether they are Kripke structure, if you observe it, you will find that both are identical, but in M 2 we are having one extra arrow, extra transition. This transition is not present in your M 1. Whether this is going to contribute something over here. If you observe it, then in M 1 you will find that this state x 6, it is not having any successor state. You just see that there is no outgoing S from this particular state x 6. So, since it is not having any successor, that means this transition relation is not complete. So, we are not going to treat this particular M as a Kripke structure. So, M 1 is not a Kripke structure. Similarly, M 2, now if you look into it, in all the states you will find that we are having transition or we are having a successor state. So, M 2 is a Kripke structure. So, we have to be careful about it. It is not like that in finite state model we can define a meaning of a CTL formula. It must be Kripke structure, and what is the basic requirement of Kripke structure? The transition relation must be complete. For each and every state we must have a successor state. So, here M 2 is a Kripke structure, but M 1 is not a Kripke structure. Now, look into Another example, say already I have explained these things. Now, by observing it also you will find that this is a Kipke structure, because if you look into all the states, all states are having a transition, or that means we are having a successor. So, now what are the three basic components? We are having set of states. So, this is S0, S1, S2, S3, this is the set of states, and the transition relation, how many transition we are having? 1, 2, 3, 4, 5, 6. So, we are having this 6 component as of transition relation, and this is the labeling function. You shall say that we are having this labeled over here, that means we are having a set of atomic proposition, and the atomic proposition that we are having here is your P, Q and R. So, S0 is labeled with P, Q, R, it says that all P, Q, R is true over here. So, label of S0 is P, Q, R. In S1, Q and P and Q is true. So, label of S1 is P and Q. Label of S2 is only R, because R is true, and label of S3 is Q and R. So, I think with this particular explanation, I think the notion of Kipke structure is clear about it, because it is having three components as the set of states, transition relation and the labeling function. And what is the labeling function? Already I have explained. Now, we are going to define the semantics of our CTL formula. So, it is like your already temporal formula I have said. Now, in CTL formula also we said that we are going to consider one particular model M, which is having these three components, set of states, transition relation L, be a model of CTL. So, now given any state S of S, now we consider any state S of S, we define whether a CTL formula phi holds in this particular state or not, and we denote it by M S phi. That means, if I am having some sort of your model M, and we are going to consider one particular state S, we are having a CTL formula say phi, we will say that M S models phi, it says that this particular CTL formula phi holds this particular state S. And similarly, we use this particular symbol also, M S does not model phi. In this particular case, what it says that in state S, your formula phi does not hold. So, basically we are going to say that phi holds in a particular state or phi does not hold in a particular state. So, in this particular case, if phi holds in a particular state, sometimes you can have a label of phi over here, and the meaning of those particular CTL formula will be defined on the structure of this particular CTL formula, because if we are going to talk a particular CTL formula, it may have sub formulas also. So, basically inductively we are going to define the meaning on this particular structure of CTL formula. Just consider one particular formula, say AFP or EFQ. That means, this is one CTL formula, this is another CTL formula. First, we should have the label of this particular CTL formula in a state. Then, if EFQ holds in say S, then we can say that AFP or EFQ also holds in this particular state, because either of these one component is true in this particular. So, if we look for one particular formula, we have to look for this particular component wise, and after that we are going to look for the entire formula. Now, that is why I am saying that the relation this M S model phi is defined by the structural induction of phi as follows. So, in general what happens, we are going to say that in every state it will be marked by this particular truth value true, and it will not mark by the truth value false, because this top represents the truth value true and bottom represent the truth value false. So, this is basically top is your true and bottom is your false. So, by default every state will be marked with the truth value true and none of them will be marked with false. That means, it says that intuitively you can say that true is true in all state and false is false in each and every state. Another one, we are going to say the second rule, MS models P if P is a member of this particular labeling function of this particular state. That means, we are going to talk about the truth values of atomic proposition. If the state is labeled with the help of this particular atomic proposition, then we say that this particular atomic proposition is true in this particular state. Similarly, if we say that a particular state S of a model M, it models not of phi. That means, the negation of this phi is true over here. Basically, it means that it does not, this particular state S or model M does not models this particular phi. So, if it does not model phi, you can mark it with not of phi also. So, already I have mentioned that basically negation of atomic proposition, we are not going to mark it, by default it is there, but in some formula we have to mark it if it is a CTL combination of CTL operators, because this will come as a sub formula of another formula. So, we need the have the root values of this particular negation. So, if it is marked with your not of phi, it means that phi is not hold in this particular state. So, these are the three basic components that we are having. So, here you just see that we are having a model. So, it is a tree structure, we have unfolded model. So, S 0, S 1, S 2, S 3. Now, if you look into this is the labeling function that we are having P, Q, Q, Q. So, M of S 0 models P, because it is labeled with P, we can say that it is models P. Similarly, I can say that M of S 1 models not of P, because it is not marked with this particular atomic proposition. So, in state S 1 it models not of P, though we are not marking it, we can say that it models not of P. So, similarly, now we can look for the root values of your this conjunction phi 1 and phi 2, whether in a model M in a particular state S, whether it models phi 1 and phi 2, whether phi 1 and phi 2 holds over there or not. It holds provided phi 1 and phi 2 independently holds in that particular state. Okay. So, we said that phi 1 and phi 2 satisfied in this particular state as provided this state models phi 1 and models phi 2. Similarly, we can look for the disjunction phi 1 or phi 2. So, since this is disjunction, so what will happen? We said that in particular state as phi 1 or phi 2 holds provided either phi 1 holds in S or phi 2 holds in S. Okay. So, these are the basic operators that we are having. So, this is your phi 1 or phi 2. So, now you look into this particular again that model that we are having S 0, S 1, S 2, S 3, and we are having these are the tree like structure and these are the labeling function that we have. Now, if we concern about this particular state S 1, we will find that M S 1 models P and Q, because this S 1 is labeled with P and Q. So, basically you can say that M S 1 models P and M S 1 models Q. Since both P and Q models in state S 1, you can say that in S 1 P and Q models. Okay. So, that means P and Q holds in this particular state S 1. If you come to this particular state S 2, you will find that it is labeled with Q, that means atomic proposition Q is true over here. So, you can say that in M S 2 models P or Q, because you just see that here either P or Q should hold in this particular set. So, here you will find that M S 2 models Q. Since M S 2 models Q, so we are going to say that M S 2 models P or Q, either P or Q. But now, if you look into that state S 2, you will find that M S 2 does not model P, because it is not labeled with your P. Since P, it is S 2 is not labeled with P, that means it is not in this particular labeling function, that means P is false, the atomic proposition P is false in this particular state S 2. Since P is false, so it does not model P. So, now if you look into this combination say P and Q in this particular state S 2 of model M, then what we will find that M S 2 does not model P and Q, because it models Q, but it does not model P. So, that is why we are saying that M S 2 does not model Q. Just you see the meaning over here. It said that S models Q 1 and Q 2 provided MS model phi 1 and MS model phi 2. So, both must be true over here. So, since in this particular state it does not model P. So, we can say that MS2 does not model P and Q. So, similarly, now we come to this particular connectives implication phi 1 implies phi 2, whether in a particular state M model M in state S, whether it models phi 1 implies phi 2 or not. So, in this particular case, what will happen? We will say that this state S models this phi 1 implication phi 2 if M S in state it does not model phi 1 or M S models phi 2. Okay. So, what we are going to say that if either models phi 1 does not models phi 1 or does not models phi 2. So, basically we said that phi 1 implies phi 2 satisfied as if in S either phi 1 is not satisfied or phi 2 is satisfied. So, either of these two conditions. So, basically we know that if we are going to talk about your some formula say P implies Q, this is equivalent to not of P or Q. So, we know that this particular implication sign is equivalent to not of P or Q. So, in this particular case, we say that if P then Q. So, if P is true then Q must be true, if P is false we are silent. So, in this particular case, if you look that P is true over here, but it is not marked with Q. So, this particular S 0 does not model P implies Q, but in this two state S 0 and S 3, you will find that it is marked with Q, but it is not marked with P. So, it is P is false over here, but we will say that if P then Q, if P is false we are least bother about it. So, in this particular set S 2 and S 3 they models your P implies Q. So, here you can find that S 2 and S 3 both models your P implies Q, because Q is true over here, P is false, either S does not models Q 1 or S models Q 2. If you come to this particular point, both P and Q are true, that means in this all condition phi 2 is true over here. So, you can say that in S 1 also it models P implies Q. So, this is the way that we are going to look for the truth values of our CTL formulas. Now, till now we see that we are discussing about CTL formula, we have defined the syntax of our CTL formulas. Now, we are going to define the meaning of our CTL formulas and what are the operators that we have in our CTL formulas. Basically, we are having all the propositional connectives and or not, XOR, implication, etc. And along with that we are having temporal operator, and if we are using temporal operator, those temporal operators must be preceded by our path quantifier. Okay, then we are going to have CTL formulas, otherwise we are going to have temporal formulas only. And when we are going to talk about CTL formula, the truth values of temporal formula defines over a state, that means these are basically state formulas. Now, when we are going to define the semantics, we are saying that CTL formulas, the meaning of CTL formulas will be defined over Kripke structure. We have seen what is Kripke structure, it is similar to finite state machines, but we are having two additional requirement. One is that transition function must be complete, and second one we are having the labeling function, that will be labeled by the set of atomic proposition that are true in this particular states. Now, we have seen how to define the meaning. So, in this lecture we have talked about the meaning or how to assign the truth values of temporal CTL formulas with respect to our this particular propositional connectives. We have seen AND, OR, negation and your these things implication and like that. Now, we have to see the how to going to assign the truth values of our temporal operators. So, next class we are going to discuss about these things. So, up till now we have talked about the truth values of our this particular propositional operators only. So, next class we are going to talk about our something called what we call as going to look for all the temporal operators. Now, you just see that now what happens, we are talking about say CTL formula, it is having propositional operator like that, or an implication and temporal operator like next state, future, until and your globally. Now, today we have seen the meaning of those particular propositional operator only. So, next class we are going to talk about this particular how to define a meaning of this particular temporal operator. Now, you just take a simple model, just say that this is my one. So, whether this is a Kripke structure, if you look into it, you will find that we are having this particular 4 state S0, S1, S2 and S3. Now, if you look into a transition relation, you will find that every states are having a successor state. So, that is why the transition relation is complete. So, we can say that this model M is a Kripke structure. Now, we just said that we are talking about a set of atomic propositions say P, Q, R. Now, the labeling function we can say that P, Q, R, P, P, Q. Now, if I give us a temporal formula, P and Q implies say R. So, if you look into this particular temporal formula, whether this formula is true in this particular, in which other states this particular formula is true, because you will find that everywhere this particular component in state S0, S1 and S2, this component P and Q is your false. You say that P is true, but Q is false, Q is true, but P is false, P is true, but Q is false. So, P and Q is false in this particular 3 states. So, since this is false, so P and Q implies R will be true in this particular 3 state. Now, when you come to this particular state S3, then you will find that P and Q is true over here. But what is the status of your R? You will find that R is false. So, true implies false. So, in this particular case, you will find that in state S3, the given formula P and Q until R is false basically, because you just see that P and Q is true, but R is false. So, true implies false, which is basically false. Now, what will happen now if we are having this particular 4 states, they are labeled with this atomic proposition. Now, when you are going to look for this particular temporal formula, then we will find that this particular formula, say if I say that this is your phi, then what we can say that this phi is true in state S1, S2, S0, S1 and S2, but it is not true over here. So, like that what we can say that now we know this particular component is true. Now, if I say that going to say that A F phi, that means we know the label of this particular phi, it is labeled in this particular state. Now, we can look for this particular truth values of this particular formula. So, prior to that we are going to see how we are going to define the meaning of F. So, in next class we are going to talk about, or we are going to discuss about how to define the meaning of this particular temporal operators along with part quantifier in our Kripke structure. Okay, thank you.